Previously, we talked about how to compute the volume of a bounded subset of Euclidean space by viewing it as the integral of the characteristic function of that set whenever that characteristic set is Riemann integrable. And then at the end, after talking about volume and working through several examples, I said, this is the definition of volume. It's fine for what it does, but it has some limitations, and one of those was a lack of additivity. So in this lesson, what we are going to do is pass from talking about volume to talking about measure, with a special focus on the idea of having a measure zero set. It turns out that will give us a better test for when, say, function is Riemann integrable over a bounded subset of Rn. Okay, so to motivate measure, what I would like to do is revisit this idea that a set can have volume zero. So in particular, what does it mean based on our previous lecture to say that a set has volume zero? Well, its volume is zero. This means that zero is what we would get if we took the set A, possibly enclosing it in some nice rectangular domain S as we've done before. And then we integrated the characteristic or indicator function of that set over this enclosing rectangle. And then for the differential here, I'm going to write dv, where if I was looking at a characteristic function, say with respect to one variable, I would write dx. Let me put a variable in here. If x is a scalar, I would write dx. If it was a region in the xy plane, I might write dA to be a little bit more specific. But in general, let's write dv. That's the volume element. Okay, so this is literally the definition of volume zero now by viewing the volume as the integral of this characteristic function of A whenever it exists. However, since we know that the characteristic function of A is Riemann integrable, that means that its upper integral and lower integral both have the value of zero, and I want to focus on the upper integral. So I'll write, let me just write A here, 1A of whatever the types of inputs we're looking at are, volume form. So this is the upper integral. There we go. New markers, hard to open. The upper integral is the infimum of the set of all possible upper sums of this characteristic function with respect to all possible partitions, as we've talked about now a couple of times. So the fact that this upper integral is zero, the infimum of the set of upper sums is zero, means that for any epsilon, given a positive number epsilon, there's a partition of, say, S. Let me write, there is a partition of the nice rectangle S, which is enclosing our domain A. This is the notation that we've used for this concept. There's a partition of S so that, I'll write satisfying that the upper sum of the characteristic function with respect to this partition, let's give it a name, p sub epsilon, is less than epsilon. All right. I'm actually going to erase this in just a moment to continue the discussion, but take a moment before I do that. And what goes into this upper sum? So I've just said the upper sum is less than epsilon. It's something between 0 and epsilon because the infimum of the set that contains this is 0. So this statement is just a statement about characterizing the idea of having an infimum of 0. What I'm asking for you to do for a moment before I come back and write it up here is take this expression and replace it with its definition. So what would it look like if I actually had the partition, had the set A, and tried to compute that manually? Picking back up where we left off, but with a little bit more room, I've kept the essential notion here, which is that for any epsilon greater than 0, there is a partition of the nice enclosing rectangle S, enclosing our original domain A, into subrectangles. So I didn't mention the subrectangles a moment ago, but make sure that you've got this down. So when I create a partition of S, we are chopping it up into a finite collection of subrectangles. That's why I've really emphasized here that it's a finite collection of subrectangles whose sides are nicely parallel to the coordinate axes, so that the upper sum of the characteristic function for A with respect to this partition is less than epsilon. If you've been watching my analysis videos, you know I almost never start with epsilon and go down in size, but it makes a little bit more sense here. What I wanted you to do a moment ago is take this expression and replace it with, I'm just going to go to the right, replace it with a sum. Given that I've actually said how many subrectangles there are, sometimes I leave that off, but it's always finite when you're looking at a partition. We can add up from I equals 1 through n the supremum for the characteristic function on each subrectangle times the volume of that subrectangle. So let me just write that out. So here, x is coming from the ith subrectangle, and then times the volume of that ith subrectangle. Okay, this is literally what it means to compute an upper sum for this function with respect to this partition. The thing is, we are not looking at a random function, we're looking at the characteristic function of A. So when I think about what could go into the soup, it's either 0 or 1, depending on whether or not there's an input from the ith subrectangle, which lives in A. So I think what I would like to do is toss all of the subrectangles which don't contain anything from A, which can happen because I could take A, I'll just sketch a quick picture, here's A, and I could enclose it in some really large, relatively large, nice rectangle S. And then when I make my partition into subrectangles, let's say I did that. Of course, some of these subrectangles don't overlap with the original domain, and that's okay. The characteristic function is always 0 on such a subrectangle, but anywhere where A overlaps with the subrectangle, it's going to be 1. So this function here is either 0 or it's 1. And so we're just going to say, throw away all the zeros, keep all the ones, just to make this look a little bit nicer. I think I'm going to say, still from I equals 1 to n, but only so that S sub I intersect A is non-empty. One of the reasons why sometimes I'm a bit lazy with my indexing when I do subrectangles is I'm like, it's always finite, and sometimes writing down the indexing itself takes a bit of thought. You can do a better job than I do in that regard. Okay, so this is saying, same partition, but this time we are only going to consider the subrectangles with non-empty intersection with the original set. So that looks like, these in here. If that's the new constraint that we're placing on the sum, that means this whole expression here can just be replaced with the number 1 and then times the volume of the relevant subrectangles. And that's all I wanted to get to on this slide. This is going to lead to our notion of measure in just a moment, but let me summarize what's key here, what we're going to extend. And that is, we are now concluding that a subset A, which is bounded subset of Rn, has volume 0 if there exists a covering of it by rectangles, which is like a finite collection coming out of a partition, whose volumes sum to be smaller than your choice of epsilon. I'm not sure I said that quite clearly enough, so let me restate. A has volume 0 if, for any choice of epsilon greater than 0, you can create a partition of an enclosing rectangle S so that the volume of the rectangles which cover A is less than epsilon. So here it's like this set, for the record, does not have volume 0, so it's not the best illustration of this idea. But it's like if I just look at the rectangles that are covering A, it's really like this notion of cover, kind of going back to like open covers and things like that. We are now covering sets with closed rectangles, closed subrectangles. If I can cover A by a finite collection of closed rectangles from this partition, whose volumes add up to being less than epsilon for any choice of epsilon I make, then we say that A has volume 0. Okay, I think I've stated it maybe 2 times, half well. Hopefully, you understand what I'm trying to say here. At the end, what we've gotten to is just adding up volumes of rectangles, and that is the number that ends up being less than epsilon in this computation. Okay, quick preview of what's about to come before I step away and let you digest this. What if, instead of saying, this finite collection that has this very prescriptive form, so this is a finite family of rectangles that came from a partition, what if we allowed for maybe rectangles which overlap, rectangles which don't have to have exactly this, style creation, and maybe even not a finite collection of rectangles. So what we're going to do in just a moment to pass from volume 0 to measure 0 is change the family of rectangles that we are going to be considering. Now that you've had a minute to read through this, let me point out some of the key distinctions between this and the idea of volume 0. Probably several of those distinctions jumped out at you, but here's one that might not have. And that is that the set A actually does not have to be bounded. So not necessarily, all right, BDD for bounded. Realistically, the context for us is thinking about domains or parts of domains of integration for bounded functions. However, even if ultimately when we return to Riemann integrating some function f, which is a scalar valued function on a bounded subset of Rn, even though that's the context we're interested in, that doesn't mean that this definition can't be extended to other kinds of sets, including unbounded sets, and we will have an example today. So A doesn't necessarily have to be bounded, and then the rest of the definition sort of flows similarly to what we were just talking about, but with maybe two key distinctions. One is, as before, for any epsilon greater than 0, there exists a covering of the set A by rectangles. But this time, the family of rectangles covering A could be finite, like coverings which are formed from partitions, but it doesn't have to be. It could be a countably infinite collection of rectangles. And then it's like once you've covered A by some family of closed rectangles, you can think of them as kind of subrectangles inside of Rn. So it's always the appropriate dimension rectangle for the space that you're working in. Whatever the covering looks like, so long as it's either finite or countably infinite, the total volume of those rectangles which are covering the set A has to add up to a number which is less than epsilon. Okay, so very similar to what we were just looking at, but like the style of the rectangles you use can look a little different, and that will make more sense once we've gone through some examples. But before we look at our first example, let me mention like some connections here between volume and measure. This is giving us more flexibility in how we cover the set A with rectangles. It includes the idea of having just a nice finite collection of subrectangles born out of a partition, which means that if you have volume 0, you have measure 0. So let me just kind of jot down here. The volume of A being 0 implies that the measure, for this we'll use the Greek letter mu, measure of A is also 0. And that's really the only implication I'm about to write down. If the measure of A is 0, that does not imply that the volume of A is 0 or that it even exists. So this does not imply that volume of A is 0. Okay, so the only implication I want to establish is that if the volume of A is 0, then automatically it makes this definition true. So the measure of A is 0, but we cannot do the converse of that statement. We will actually start with the rationals. We could focus on, say, the rationals just between 0 and 1. That's a set that we proved had no volume, meaning that there was no number we could reasonably associate and say, this is the volume of the set. In other words, the characteristic function of the rationals between 0 and 1 is not Riemann integrable. However, we will prove in just a moment explicitly with a covering that actually the entire set of rationals on the whole real number line has measure 0. So it's just a really different result than what we had when we considered the volume of that set. I want to say here that I'm only focusing right now on measure 0. So we are not going to look at, say, sets of irrational numbers during this discussion, because then we might have a positive measure, and we have not defined positive measure. So the focus right now is on measure 0 sets. In this video, this is the only example of computing that a set has measure 0 that we will do in full detail, because next I will give you two results that will allow us to look at sets, including this one, and immediately say, this has measure 0. So this example will actually be covered by a result in just a moment, but I think that this is illustrative. And also, it's like this proof will inform how we prove the general result. Okay, so what I would like to do is show that the set of rationals on the whole real number line, so it's an unbounded set, satisfies the definition of measure 0. That means my proof is going to sound like the definition of measure 0. I'm going to start by saying let epsilon be greater than 0. So let's fix some positive number epsilon. Again, that's like the beginning of the definition of measure 0. Next, I need to create the covering. In order to do that, I'm going to point out to the reader that the set of rationals is a countable or denumerable set. So let's kind of list it out. So since Q is denumerable, I'm using this word instead of countable, which I usually say, just because whenever I kind of say the set can be listed out, I tend to go to denumerable. Okay. We can list out the rationals. So we can list out the set of rational numbers as a first rational number, followed by a second rational number, followed by a third one. And we'd have to do that forever. But what makes a countably infinite or denumerable set special is that there is some way to enumerate the elements. So it's like, while I would never be able to stop writing, if I could keep going like this, I would eventually write down every rational number. Okay, and then that gives us a way to talk about specific elements. I'm going to take each rational number and manually place it inside of a subinterval on R. For each R sub I, maybe I should say for each I in the set of natural numbers, enclose R sub I, the ith rational number on our list of rational numbers, in some subinterval, and I'm going to give you a form for it. Enclose R sub I in S sub I, that's the name of the subinterval. And it's going to look like R sub I on the left through R sub I plus epsilon over 2 to the I plus 1. Okay, a couple of remarks to make. One is that if you think about the way the subinterval looks on the real number line, the rational number in question is on the left side of it, and that might feel unsatisfying because often we like to think of things as kind of on the inside, but that's okay. This is a closed subrectangle on R. It's a closed subinterval, and R sub I is being covered by the subinterval. It's right on the edge. It feels a little weird, but it's okay. And then the second thing I want to point out is this epsilon over 2 to the I plus 1. You'll see why we even have this kind of expression in just a moment. But the plus 1 here, this is going to allow me to get strict less than epsilon an inequality at the end. If I were just writing this from scratch and I hadn't kind of worked through it this morning, I probably would have put down epsilon over 2 to the I and then maybe made this adjustment at the end. So this is the kind of thing that once you've seen this proof, you'll look for this type of expression. Okay, let's say what the volume of the subinterval is as a subset of R. I'm going to use the volume notation, even though it's really just the length of the subinterval. Notice, sticking with the notation from the definition, the volume of a subinterval of real numbers, of course, is the length of it. So let's do right point minus left point, and that's going to just be this number. Each rational number is being covered now. We have a family of subintervals covering all of the rational numbers. There's some overlap, but that's okay. This doesn't have to look like a partition. It's just a covering by closed intervals. Therefore, Q is covered by, let me say, this family, where here we need all of them. So this is an infinite covering, but that's okay. It's still countable because for each rational number, we get one of these and vice versa. And Let me hesitate for just a moment. I'm going to pause because I want to give you a chance to maybe write this down, digest it, see if you can do the summation of the volumes for all of these S sub I. You should notice something. So it should give you a sum that you can actually compute. And once you see that, you'll realize why this piece has this particular form. I hope what you recognized happened is that the summation of all of these volumes produces a geometric series, and that is what you want to do. Anytime you have an infinite sum, it's like even if you know an infinite sum converges, it can be extremely tricky to know what it converges to, and therefore that you can put a bound on the sum. Unless you're working with a geometric series, that's really the most elegant kind of series to have in this context. So the way that I did this, we're going to add up numbers of these forms. Those look like terms in a geometric series. Let's do it specifically. So from I equals 1 through infinity going across the natural numbers, we are adding up all these volumes. I'm just going to go ahead and I'll put in this. So just like in the definition, let's do this summation of volumes. And that's going to be, let me just write the epsilon in front. That's just a coefficient. And then we have 1 over 2 to the I plus 1. It's not maybe the most textbook looking form for a geometric series, but here's the general rule of thumb for doing a geometric series. If you recognize, okay, this has the form of a geometric series, but maybe my indexing is a little bit non-standard relative to the definition of a geometric series where everything is indexed perfectly, you can always add up an infinite geometric series regardless of where it starts or exactly what's going on here. If you do first term divided by 1 minus what I would think of as the radius. So the first term, when I plug in I equals 1, is 1 over 2 to the 2. So 1 over 2 squared. Okay, so that's the first term. Divided by 1 minus the radius here, that's going to be 1/2. So 1 minus 1/2. Okay, so I have 1/2 squared divided by 1/2, so that's 1/2. This is epsilon over 2. I can tell you that these subrectangles have a length, if you compute all their lengths and add it up, it literally adds up to exactly epsilon over 2. The definition of measure 0 is less than epsilon, and that's why I have this plus 1 here. So it feels a little bit pedantic, but it does make it work. Okay, and I think I will wrap this computation up there. Despite the fact that rational numbers are uncountable and unbounded, something that we did not look at when we talked about volume, we can enclose each rational number in its own closed bounded interval, whose length we can compute immediately, so that we think of as the volume of a subinterval of real numbers, and then add up all those lengths. By construction, it's a geometric series. Look to do that if you're doing this kind of computation. The lengths add up. I added an extra factor of 1/2 in here to make it perfectly match the definition of measure 0, and now we've proven that all rational numbers have measure 0. Up next is a couple of results that will allow us to perhaps get to this like through a theorem instead of manually. But I think this is a good example to see. Now I would like for us to prove this theorem. Any countable collection of measure 0 sets has measure 0 in its own right. We'll talk about how we could use this theorem, say, to address the question of the rationals that we just looked at the end. Let's jump right into this proof. Once again, I want to prove a set. In this case, it's a countable collection of sets. I want to prove the grand set has measure 0. It's going to be a direct proof that sounds exactly like the definition of measure 0. So let's open with let epsilon be greater than 0. I wanted to start by just looking at the rationals because that proof gets us ready for this proof. In fact, you'll see looking at the two proofs together that there's a theme there. There's an attack strategy that you can have if you're trying to manually show that something has measure 0. Okay, so let epsilon be greater than 0. We have here a countable collection of measure 0 sets. It's countable, so just like we did with the rational numbers, let's list out the sets. So before it was rational numbers, here it's sets. List out the sets as, we don't know if it's a finite collection. I guess if we say countable collection, it kind of implies countably infinite, but I'm just going to say A1, A2, A3, etc. Consider the jth member of this collection. We know that this set has measure 0. So each of these sets in their own right is a measure 0 set. As the measure of A sub j is 0, it satisfies the definition of a measure 0 set. So I know that there's a good covering of this by rectangles. I just need to be sure that my indexing is good. So let's say as the measure of the jth set is 0, there exist I'm going to write suitable covering of A sub j. There's the suitable covering of A sub j by rectangles. Let's index this as j is fixed, and then k, my second subscript here, will index us through this family of rectangles. So like j goes with this j that's fixed in this statement, and then k takes us through however many rectangles we're using to cover A sub j. So that there exists a suitable covering of A sub j by this collection of rectangles so that the sum over the index k, so going across the family of rectangles, of their volumes is less than, just like with the rational numbers, we're actually building up something that's going to turn into a geometric series. So I believe what we want to have here is epsilon divided by 2 to the j plus 1. We can always adjust this a little bit at the end to make it work out perfectly, but I think that this should work for us. Okay, when I say suitable here, it's not technically defined here, but I mean finite or countably infinite. I just didn't want to write that out. Okay, so since we have a measure 0 set, there exists a family of rectangles. It's either a finite collection of rectangles or it's a countably infinite collection of rectangles, so it's a suitable collection of rectangles whose total volumes add up to be our already fixed number epsilon divided by this number. Notice we're summing across k. Just be careful here with how you index. So k is running through the rectangles, j is fixed. J corresponds to this fixed subscript referring to which of these sets we're currently analyzing. And then it's like the bound on the sum is therefore in terms of j. All right, there's not much else for us to do except say just gather all of these rectangles together. So here's a family for the jth set, but we have countably infinitely many of these sets. Just consider all of the rectangles. So for all of these sets in the collection, how about then the collection that we're looking at is covered by the union of all of these families. I think I will write S sub j comma k, where that's going to go through all pairings of j with k. And let's add up the volume of all of these sets. So it's really going to be like a double sum. And what I'm going to do is say, literally, it's a double sum. Add up across j, add up across k, this. I'll analyze this double sum in just a second. No, sorry, I wrote that wrong. What I need to first put in is just the volume. This. Okay, let's pause here. This is the total volume of all of the rectangles covering A sub j, and then do that for all of the sets in this collection. So it's like when j equals 1, what's the volume of the family of rectangles covering A1? Add to that, when j equals 2, we're going to add the volume of all the rectangles covering A1 and A2. And then add the volume of the rectangles covering A3, 4, etc. That's why J comes before K. So this goes with the jth member of this collection. And then it's like, then add up all of the collections for each of these. But we know exactly what this inner sum should be. So we have like an iterated double sum here. The inner sum by construction is less than epsilon divided by 2 to the j plus 1. So I'm going to go up in size by saying this part is less than epsilon over 2 to the j plus 1. Add up over j. And then that's going to be, all right, less than or equal to, same idea as before, epsilon times 1 over 2 squared. It's actually the exact same computation as before. And this is epsilon over 2, and that's less than epsilon as desired. I'll stop writing here and then talk through this. Okay. Here, the reason why I wrote less than or equal to instead of strictly equal to, passing from what looks like a geometric series to the sum of that geometric series, is I don't actually know necessarily that J isn't finite. I mean, that we're not going across 10 sets here. So I just thought if it was 1, 2, 3, 4 off to infinity, this would actually be equality. But this proof and the statement will work if we have just a finite collection of sets. So I just wanted to allow us to have potentially only 50 such sets. Okay, so yeah, that is why I used an inequality here. Turns out, actually, since we have a less than here, we didn't need this extra factor of plus 1, but it didn't hurt anything. So now we have said that this, collection of measure 0 sets itself has measure 0. And that is a nice thing to see. That's something that we didn't see with volume. Before I continue talking about implications of this theorem, actually, let me pause, step aside, let you digest this, and then we will discuss how we can use this theorem. When we looked at volume at the very end of that lesson, I pointed out that the volume of a singleton point on the number line is 0. So if you just say, what's the volume of 0 on the number line? It's 0. But we could take a countable collection of singletons and arrive at a set that had no volume. The example of that was the rationals between 0 and 1. Now we are saying you can't do that with measure. Any countable collection of points, therefore, must have measure 0, including the rationals, as we just proved explicitly. So any countable set of points has measure 0. We now know that. So if you can describe a set that way, you're done. If we'd done this before the exercise with rational numbers, we wouldn't have needed to do that proof at all. We could have just cited this result. So that's one thing I wanted to point out, that you can now apply this result to any set that you recognize as a countable collection of measure 0 sets. The other thing I wanted to point out is that saying, any countable collection of measure 0 sets itself has measure 0 is like a better additivity statement than what we essentially did not have with volume. So it's this nice way of kind of gluing things together and feeling like you're preserving a property. Okay, I have another result for us to look at. The second statement is very fast. It falls right out of the definition of a measure 0 set. So I claim this really needs one line for a proof. We're just going to jot down a couple things in a second. However, give yourself this as an exercise for a moment. So go ahead and pause and see if you can realize why this is implied immediately by the definition of measure 0. It comes down to the idea that any suitable covering of the larger set also covers the smaller set. Let me just put down a few statements just symbolically. Suppose that A is a subset of B, and we know that the measure of B is 0. So B has measure 0. If some family of rectangles Si is a suitable covering of B, then it's also a suitable covering of A. And that's it. If you're writing this up more formally, you'll want to say a little bit more than this, but this is the idea. So if B has measure 0, then that means you can cover it by some nice covering of rectangles S sub I. Those same rectangles cover any subset of B, so any subset of a measure 0 set also has measure 0. Okay, I'm going to wrap this lesson up here, but we have more to come. And in particular, we'll keep working with this idea of measure zero sets, and it's building us up to Lebesgue's theorem. Thank you for your attention.